Hey, welcome to high school chemistry. My name is Rex. Today we're going to focus on chemical formulae, molecular formulae, and radicals. Then we're going to focus on RAM, which is relative atomic mass, RMM, which is relative molecular mass, and moles and molar mass. First of all, let's talk about chemical formulae. A chemical formula of a molecule is when we're talking about the symbols and the elements the molecule consists of. Before I explain this, I want you to know that at around 1814, someone called Berzelius had a good idea of naming the elements according to symbols. Whether the symbols were using of capital letters or capital letters and a smaller letter, Berzelius suggested using symbols to represent elements. So here's how it's represented. If I was talking about nitrogen, for example, we can use the first letter of nitrogen, which is N. And so the element N is nitrogen. But then what if we came across another element that has an N, for instance, sodium? We don't write sodium in the periodic table as S. S is for sulfur. We write sodium in the periodic table as natrium. Natrium is the Latin name for sodium. So sometimes we use Latin names for some elements in the periodic table, like natrium, which is for sodium, or kalium, which is for potassium, or aurum, which is for gold, or ferrum, which is for iron, or plumbum, which is for lead, and so on. But sodium, the Latin name for sodium is natrum. And natrium has N in it. So you wouldn't just go and write N because nitrogen has already taken that place. So you write N and then the next letter following N, which is A. So Na is the element sodium. Anywhere you see Na, if you tell any chemist what is Na, the person already knows it's sodium. So I'm going to list out 20 elements of the periodic table. For you, it's just memorize and keep it in your mind because I might bring up some of these elements. So there's hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, alright, I'll just stop at 15, alright? This is already enough for us to use and explain the RAM, RMM, moles, molar mass, and chemical formulae. So here we have hydrogen, helium, and the rest. So now, when we're talking about chemical formulae, we're listing out the element and how many times the element appears in a molecule. But we don't normally go to the details of that chemical formulae. So, you know what, on the other hand, I'm going to list out the 20. So I've listed out 15, I'm going to list out 5 more. So there's sodium, magnesium, aluminium, silicon, phosphorus, and there's sulfur. So you know I'm going like this, like this, like this, and then here I go like this. Sulfur. Sorry, that's not the spelling of sulfur, it's F. Sulfur, chlorine, argon, sulfur. Sorry, I wrote an L, I just realized that. Sorry, it's supposed to be sulfur. Sulfur, chlorine, argon, potassium, and calcium. So these are the first 20 elements of the periodic table. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. You can take them in any order you want. The order of the elements on the periodic table isn't really important to us right now. I'm just listing out the first 20 elements. But if you like, you can also take them in order. It goes like this and stops at boron. So I'll just give it a mark so you know where to stop and start from. And then it stops at neon again and stops at phosphorus before we now go back to sulfur, chlorine, argon, potassium, and calcium. So you can pause the video and pen this down if you don't already know the first 20 elements of the periodic table, and you can also screenshot it. I'll give you a moment. Okay, so when we're talking about chemical formulae have to deal with the number of times an element appears in a molecule. So I'll assume that you've taken this down, so I'll clean it off and create some space for me to solve some questions, or give some examples rather. So when we're talking about, for example, H2O, this is a chemical formula. It only tells you how many times hydrogen appeared and how many times oxygen appeared. But what about molecular formula? Well, molecular formula now goes to the details of how many times an atom of an element appeared. So let's say we're talking about H2O. A molecular formula would be like, it's 2 atoms of hydrogen and then 1 atom of oxygen. Alright, I'll just give it an A so you'll know it's an atom, not an element. So this is the chemical formulae, this is the molecular formulae. That's the difference. Alright, you already know that there are 2 hydrogen atoms, which will give you H2, and then there's 1 oxygen atom. But what about radicals? Or there are some times that, some atoms or molecules, would come together and would be known as one particular element. So that doesn't mean that they're not a molecule. It just means that we treat them as a particular, we treat the molecule as one. So let's say we're talking about hydroxide. Hydroxide is OH minus. This means that we treat OH, which is oxygen and hydrogen, both combined together to give us a negative charge, which means that oxygen and hydrogen came together and we got OH, which is hydroxide, and it has a negative charge. So this is an anion, alright? And it's 1 negative charge. As you can see, this is 1 negative charge. So the hydroxide is treated as, the molecule is treated as 1 atom. It isn't 1 atom, of course, because we have oxygen and hydrogen, but we treat it as 1 atom when it comes to ordinary chemical processes or when it's being combined with other elements. For example, there's something called sodium hydroxide. Sodium hydroxide is sodium plus hydroxide, and hydroxide here is OH minus. So combine that with sodium, which is Na, so Na plus OH minus is going to give you NaOH. This is sodium hydroxide. There are several radicals that you have to memorize. They are very important. There's nitrate, there's nitrite, there's hydroxide, there's bicarbonate, there's acetate, and there's even permanganate. But these you have to memorize them because they're not going to give them to you when you're doing exams or you're taking tests. You have to keep them in your brain. It's a must. Alright, so we've talked about chemical formulae, molecular formulae, and radicals. So we're going to talk about relative atomic mass, relative molecular mass, moles, and molar mass. We're going to talk about the relationship between moles and molar mass as well. So what is the relative atomic mass of an element? Before I define that, I want you to know that we use a reference. We reference the relative atomic mass of an element to another atom called carbon-12. Now, carbon-12 is an isotope of carbon. It's supposed to be carbon, but there are 2 isotopes of carbon. There's carbon-12 and then there's carbon-14. But carbon-12 is the most abundant and it's the most stable. And so that carbon-12 is what we use as a reference for the mass of other elements. So when we're talking about the mass of another element, we're talking about that mass divided by the mass of 1/12 of carbon-12. So if you want to talk about what is the mass of oxygen, the mass of, let me write this bigger. When we're talking about the mass of oxygen, alright, the mass of oxygen, to find the mass of oxygen, you have to divide that by 1/12 of carbon-12. Alright? Before, scientists used to use hydrogen-1 for that matter, because hydrogen was at that time the smallest or the lightest element, so it was used as a reference point for other elements. For instance, since hydrogen was the lightest element, you could say that oxygen was 16 times heavier than hydrogen, so oxygen has 16 atomic mass units, or AMU. That is the unit we use for measuring the mass of atoms, or molecules, or elements. So you could say that oxygen is 16 AMU because oxygen is 16 times heavier than hydrogen, or that carbon is 12 AMU because carbon is 12 times heavier than hydrogen. Or you could say that calcium is 40 AMU because calcium is 40 times heavier than hydrogen. But carbon is the most stable, so that is the one scientists use today. And so when we're talking about the mass of oxygen, we're talking about the mass of oxygen divided by 1/12 of carbon-12. And carbon-12, the weight of carbon-12, or the mass of carbon-12, is exactly 12 atomic mass units, or 12 AMU. So anything respective to 1/12 of 12 AMU is the mass of that element. So from what I just wrote now, the AMU for oxygen is 16 AMU. Alright? So the AMU for oxygen is 16 AMU. I'll just call this oxygen. The one for hydrogen is 1 AMU. The one for carbon is 12 AMU. So just keep this in mind. This is how we measure the relative atomic mass of elements respective to carbon-12, or 1/12 of carbon-12. So when we're talking about relative molecular mass is different in the sense that we add up how many times an element repeats itself based on the relative atomic mass. So here's some examples. What is the relative molecular mass of H2O? Remember, I said that the relative atomic mass of oxygen is 16 AMU, and I talked about that the relative atomic mass of hydrogen is 1 AMU. So from this, we can actually find out the RMM, or the relative molecular mass of H2O. How do we find that? How many hydrogen atoms are in this molecule? 2, right? So we're going to add up 2 AMU because hydrogen repeats itself 2 times. So we're going to be like, to add this up, we're going to get 1 multiplying 2, so 1 AMU, which is the mass of 1 hydrogen atom. 1 AMU multiplied by, it repeats itself 2 times, and then we add that to 1 oxygen atom, which is 16. So 1 times 2 is equal to 2, and 2 plus 16 is equal to 18. This is 18 AMU. This is the relative relative molecular mass of water. And here's another example. Have you ever heard of carbon dioxide? I'm pretty sure you have. So carbon dioxide, or sorry, let me say carbon 4-oxide. Carbon 4-oxide, right? This is carbon 4-oxide. So oxygen, there are 2 oxygen atoms in this molecule and 1 carbon atom. Carbon contains 12 atomic mass units, and oxygen contains 16 atomic mass units. So from this, we can solve the relative molecular mass of carbon 4-oxide. First of all, carbon is 12. So because carbon only repeats itself once, we're going to have 12 plus oxygen repeats itself 2 times, so 16, which is the mass of 1 oxygen atom multiplied by the 2 times it repeats itself, is going to be 12 plus 32. And 12 plus 32 is going to give you 44. So this is 44 AMU. This is the relative atomic mass, or sorry, keep making that mistake, the relative molecular mass of carbon 4-oxide. Okay, so now we're going to focus on moles. Mole is it's not a mole as in a furry animal, and it's not a mole on your cheek. No, I'm talking about moles in chemistry, and that is a totally different and very interesting aspect of chemistry. You know how you use a dozen to classify 12 eggs, or you use a score to classify 20 things? So if you say I have a score of something, you have 20 of that thing, or you have a dozen of something, you have 12 of that thing. So that is how we use moles in chemistry. We use moles as fundamental units to calculate how many atoms are in a particular substance. Alright, because you know that particles such as atoms and molecules and ions are very small, and you can't actually handle them, you can't actually count them. In a drop of water, there might be millions and millions and billions of atoms, and we can't even see atoms through an electron microscope, even though an electron microscope can magnify an object to 200,000 times its normal size. So if we can't see an atom, even though we use an electron microscope, how are we able to count these atoms? We use moles. So we use moles with respect to Avogadro's number. Avogadro's number was discovered by Amedeo Avogadro, who was an Italian chemist. He discovered and postulated his number of the mole. So the mole is like saying 1 mole of a substance let's say 1 mole of oxygen, which I'll call O, is equal to Avogadro's number. Avogadro, not avocado. Don't get that mixed up. Avogadro. Avogadro's number. So, whenever you see 1 mole of a substance, just know it contains Avogadro's number. And what is Avogadro's number? Avogadro's number, which I'm going to call A, is 6.022 times 10 raised to the power of 23 particles. It means that 1 mole of oxygen contains exactly 6.022 times 10 raised to the power of 23 particles. It's like saying if you want to find out how many atoms are in 1 mole of oxygen, you don't need to start counting them. All you need to know is that if you have 1 mole of oxygen, the atoms in 1 mole of oxygen is practically just 6.022 times 10 raised to the power of 23 atoms. That is the number of atoms that 1 molecule of oxygen contains. From this molecule, from this mole and even molar mass, which I'm going to define now, we're going to find out the relationship by changing the mass of an object in grams to its molar mass, and then find the relationship between molar mass, the mass of an object in grams, and moles, and how we can work out some examples and change them to particles, or how many atoms are. So if we're talking about maybe a substance that has the size that its mass is in grams, we can do a lot of conversions and find out how many particles are in a certain gram of a substance. So I'm going to define molecular mass. Molecular mass is just like relative molecular mass, which is, not molecular mass, molar mass. Molar mass is just like relative molecular mass in the sense that it uses the AMU reference, which is that average size of an atom respect to 1/12 of carbon atoms. That is how we were finding the relative molecular mass, and that's the same thing with molar mass. The only thing with molar mass is that molar mass is, let me write that as M. Okay, let me just write molar mass. Molar mass is how many grams of a substance are in 1 mole of a substance. So molar mass is measured in grams per mole. Just know that anytime you're talking about molar mass, it's grams per mole. So in relative molecular mass, we were using AMU, which is atomic mass units. But in molar mass, we're using grams per mole. It means how many grams are in 1 mole. And we can twist this formula in the sense that we can make mole the subject of the formula. So if you want to find mole and you're given the molar mass and the mass in grams, you can find the mole. Or if you want to find grams, you can make grams the subject of the formula and find grams if you're given the mole and the molar mass. So I'm going to I'm going to solve some examples so that we can get clear with what I'm talking about. So I have a question here. This question says, how many moles are in 12 grams of carbon? And this is the molecular mass of carbon. Remember, the molecular mass is how many grams, or the mass of a substance divided by its mole. So that's gram per mole. So whenever you see gram per mole, know that it's the molecular mass. Sorry, the molar mass. I keep getting that wrong. But it's molar mass. So this is molar mass, all right? And this is the molar mass of carbon based on the relative molecular mass of carbon, which is 12. So how do we find moles if we're given grams and molar mass? Remember, I just told you that molar mass is equal to how many grams of a substance, which is G, divided by 1 mole of that substance, right? And now you're given the mole and given the grams, you're given the mass, the molar mass and the grams, and now you want to find the mole. All you need to do is just make mole the subject of the formula. So let's do that. I'll call molar mass M, capital M, and I'm going to call mole lowercase m. So let's make that the subject of the formula. So capital M is equal to G over lower m. To make this the subject of the formula, I cross multiply. So I get capital M multiplied by lowercase m is equal to the grams. And then to make lower m the subject of the formula, I divide both sides by molar mass. And so from this, I already made the mole the subject of the formula. So mole is gotten by the mass divided by the molar mass. So here we can say that mole is gotten by the mass divided by the molar mass. Alright? So we have the mass, which is 12 grams, and we have the molar mass, which is 12 grams. So 12 grams per mole. So 12 cancels 12, and so therefore, this is 1 mole of carbon. Woo, we've explained our first question, and when I talked about moles, we've already just gotten 1 mole of carbon. So this is 1 mole of carbon. If you have 12 grams of carbon, and you know that carbon has 12 grams in every mole, and you just have 12 grams, you already know that that is 1 mole of carbon. And if we were to change this into how many atoms are in 1 mole of carbon, what would I do? Remember I told you that there's a chemist called Amedeo Avogadro who came up with a number that can change a mole to particles, or to atoms, molecules, ions, elements, that kind of stuff. So to change 1 mole of carbon to particle, you have to multiply 1 mole of carbon by Avogadro's number, which is 6.022 times 10 raised to the power of 23. So if you multiply 1 mole times 6.022 times 10 raised to the power of 23, you're going to get 6.022 times 10 raised to the power of 23 atoms in just 1 mole of carbon. That question was easy, but let's get to the harder questions. And here I have another question which says, calculate the mass of 0.25 moles of oxygen gas. O2 is oxygen gas. And they said here that the molar mass of oxygen is 16 grams per mole. Now, we talked about finding the mass. They've given us the molar mass and they've given us the moles. So how do we find the mass? Let's write out that relationship again. So molar mass is gotten by the grams, or the mass, divided by the mole. They've given us the mole and they've given us molar mass, and we're looking for mass. What we need to do is to make mass the subject of the formula. And to make mass the subject of the formula, I'm going to cross multiply mole with molar mass. So if we make mass the subject of the formula, the answer would be mass, or to find mass, you have to multiply the molar mass by the mole. Alright, so we have the moles, which is 0.25, and we have the molar mass, which is 16. So we're going to find 0.25 of 16 grams per mole. But remember that we can't just write 16 grams per mole, because remember, this is oxygen gas. And oxygen gas contains 2 atoms of oxygen in its molecule. So this oxygen gas is still 16. It's just one. So they're saying for every oxygen atom, you're going to get 16 grams per mole. But this is 2 oxygen atoms in 1 molecule. So you're going to multiply 16 by 2 to get 32. So 16 times 2 is 32. So in this molecule of oxygen gas, it's actually 32 grams per mole. So just keep that in mind. 32 grams per mole. So what is 0.5 multiplied by 32 grams per mole? Well, 0.5 as a fraction is 1 over 4. So what is 1 over 4 of 32? Well, 4 can go in itself once, and 4 can go in 32 8 times. So therefore, the mass of the oxygen gas is 8 grams. You see, this is actually pretty easy. All we need to do is that we have to find the relationship between molar mass, and the mole, which is that molar mass is equal to the mass divided by the mole. And if you have that relationship, if you're given the molar mass and the mass, you can easily find the mole by making it the subject of the formula. If you have the mole and the molar mass, you can find the mass by making mass the subject of the formula. And if you have mass and the mole, you can find the molar mass by making molar mass the subject of the formula, which it already is. But anyway, what we just did was basically multiply 16 by 2, because we have 2 oxygen atoms in its molecule, and we therefore had the molar mass and the mole. So all we needed to do to find the mass was basically multiply the molar mass and mole after we made mass the subject of the formula. And the molar mass, which was 0.25 or 1 over 4, multiplied by the mole, which is molar mass, which was 32, multiplied by the mole, which is 0.25 or 1 over 4, gave us 8 grams. And here's the last question. How many molecules are in 3 moles of water, or H2O? Now, we talked about changing moles to particles using Avogadro's number. And we said that if you have the number of moles of a substance, you can change it to how many particles that substance is by basically multiplying it by Avogadro's number. So let's do that. We have 3 moles of H2O, or 3 moles of water. Now to change this into molecules, which is a particle, we just need to multiply 3 moles of water by Avogadro's number, which is 6.022. And this is where you have to grab your calculators, guys, because this is a very complex calculation. So 3 multiplied by 6.022 times 10 raised to the power of 23, that's Avogadro's number, will give you 1.8066 times 10 raised to the power of 24 particles. Or, to be precise, 1.8066 times 10 raised to the power of 24 molecules. Alright, it was pretty easy. All we needed to do was multiply the number of moles by Avogadro's number to get the number of particles, which was 1.8066 times 10 raised to the power of 24 molecules. So guys, I have one more question with me, but I was planning to solve it, and then I thought about it, and I said I was going to give you that question to solve it by yourself, and let me know in the comments. So the question is, what is the number of moles in 100 grams of sodium chloride, or NaCl? And the molar mass of NaCl is 58.5 grams per mole. I'd like you to pause this video, take this down, solve it, and write your answer in the comments below. If you enjoyed this video, please like, subscribe, and share with at least 3 people who you know don't have access to basic education or who is bold enough to explore homeschool, and I'll see you in the next class.